time every single one.
Okay,
This is exhaustive, sorry.
so let's begin the last lecture. So we learned about expectation maximization last time, and it started out looking like something kind of undecipherable, but then essentially we explained it by taking the log likelihood, which is what we want to maximize, and we wrote it in terms of three things. This term here, which still looks a little bit unexplained, but then the entropy, which has some meaning, and then this last term, which is the Kullback-Leibler divergence, which we know is positive. And so what that says is if we get rid of this term, that means this is smaller than the likelihood because we've gotten rid of something that's non-negative, or it's at least this is a lower bound to the likelihood. And so that gave us this interesting scheme where we iterate between tightening the lower bound and maximizing this. And so we have this picture of, imagine that this is our log likelihood. We're adjusting a single parameter theta. And so first we have a guess of theta here. We tighten the lower bound, which means, and in this picture, the lower bound is always constructed to be quadratic. So we're finding the quadratic that is perfectly matching our likelihood at this value. But then this otherwise is a lower bound. Otherwise, it's less than the likelihood. So because it's a quadratic, it's easy to optimize. So we immediately can compute the peak here, and then we repeat. So next we find a lower bound, which is going to be tight here. Maybe it looks like that. We find its maximum, and that gives us a new point. Find that lower bound, and so on and so on. Eventually, we converge to the peak of the likelihood. So that's the technique, these two steps. And so now the details would be, all right, how exactly do we maximize this lower bound? Well, we said we can set it exactly to equal, or how do we tighten the lower bound? We can set it exactly equal to 0, the smallest possible value, by making this equal to this. And so that's exactly what EM does. It sets this p hat to that distribution. And then the second step is, how do we maximize this? Well, if we're maximizing over theta, this term doesn't matter. So we just need to maximize this, and that's exactly what EM does in the M step. So finally, we have this explanation for expectation maximization. So the only things we have to do now is we have to apply this procedure to our Gaussian mixture model. And then we'll show a demo of this, and then we'll be done. Okay, so Gaussian mixture model, let's remember what we were doing with that. So come back to here. So Gaussian mixtures, basically we have some data like these dots, and we want to fit a mixture of Gaussians. So it's like a set of different Gaussians. Each one has a different mean, which tells us its center has a different covariance, which tells us how it's stretched, and has a different height. And the heights are essentially adjusted by these gammas. And the heights should be proportional to the number of samples that are explained by that Gaussian. So that's the Gaussian mixture. And so our objective now is, given a data set of X values, to come up with the maximum likelihood fit of all of our parameters. And we're going to use EM for that. But let's look at some of the key expressions. This is one of the key equations that we'll see again today. So this is the probability that the data point xi came from cluster K. It has this form. So you can see it's this ratio of a single Gaussian and over a sum of Gaussians, and here we have like all the Gaussian parameters there. That's one important equation. Let's see, another important equation is this one. The probability that So kappa is kappa is the random variable that tells us which cluster it comes from, and the probability that kappa equals k is our explanation for gamma k, and then the other important equation is basically this. So if you tell me kappa, if you tell me that kappa is k, I know I'm coming from the kth cluster, so now the probability of x is just that Gaussian. Okay, so we have, those are the main equations. Those are what we're going to use with expectation maximization. So we have everything we need to do to start. Okay, so we come back to EM, and for EM there was this function called Q that had in it the parameters that are free variables that we want to optimize. We want to maximize these in the M step. And then these are our whatever guess we have that we figured out in the previous iteration. Okay, so this is the form of the Q function. So the key thing now is we have to choose our hidden variables. Z was a hidden variables, that's what we called them for EM. But we know for Gaussian mixture modeling, our hidden variables should be our kappas. So that thing I called the Z matrix is now just a vector of kappas. And let's remember that each kappa is actually a discrete number. It's an integer between 1 and k. So I rewrote the definition of Q. Instead of Z, I put in kappa everywhere. So now we have to try to simplify. So the first thing we see is here's our data. It's the joint distribution of our data samples X and our kappa random variables. So we're going to assume that all our Xi's are independent, as are our kappas. So kappa I is telling us essentially what's the probability that Xi came from some particular value k. So we're just going to assume that both of those things are independent across our data samples. That means that this is a product distribution, product over I of this stuff. Okay, so that's nice because that's our first simplification. So now, as we know, the log of a product is the sum of the logs. So let me do that here. I'll scratch these out. So that's now the sum of the logs. I have to put the sum out here. Okay, so we have sum of these things. So there's another simplification we can make. So let me see if you guys can figure this out. So notice that this integral is a multivariable integral. So there's a whole vector of kappas. So really this is like a multidimensional integral over n different numbers. So can we simplify that? Can we make that single variable integral? So how do we do that? What's the logic? So notice that the whole vector of kappas is appearing here, but there's just only a single kappa I appearing here. You see what we can do? Yeah.
The function, the log of the likelihood is non-zero only for the ith index when we consider like pi. So the integral of 0 is 0 when we consider only like one index.
Okay, maybe that's one way to think about it. Okay, the way I would explain it is let's break the integral into an integral over kappa I, and let's move this guy log pxi kappa I theta in there, and let's have another integral which is all over all the other kappas not I. So I'll write that kappa vector backslash I. That's kappa not I. And there, I'm going to write what remains. This is p kappa given x given theta t. Okay, so sorry I'm running out of space. Maybe I can shrink this. Oops. Okay. Okay, so we have over here, I'll just write this d kappa not equal to I, d kappa I. Okay, so what we've done is we're now treating the kappa I a little differently than we're treating all the other kappas that are not I. Do you see how this is going to help us? What do we get when we do this?
Just be 1 minus the probability of like kappa I.
So this is a density that has many random variables, many different kappas in it, right? If I integrate out all but one, what remains? So like, let me write it in a simpler way. If I have P, A, B, and then I do DB, what do you get?
P of A.
P of A, right? So basically, this is kind of what we have here, except in this case, we actually have like n different variables, and we're integrating out n minus 1, but what remains is the only one we didn't integrate out. So this will reduce all the way down to P kappa I given x theta k. We integrate out all of them except for, we can just integrate out all of these variables. And now our lives are much easier because I just have a single scalar integral. I don't have a multidimensional integral anymore. Okay, does everybody see that? So that's how we got here. So this changed to this. So now our lives are a lot easier. Okay. Okay, the other thing that's a little bit weird that I've been doing is I have a discrete random variable and I've been integrating over a discrete quantity. So you can handle this if you work with delta functions. So if you write the density of kappa as a pulse train, so this is like P kappa I, and the pulse train comes alive at integers 1, 2, so on up to k. So in that sense, if you write it that way, this is valid. But there's a simpler way of writing it, where we actually just treat the kappa i's as discrete. Let's just write it as a sum. So now what we're really saying here is this is like the probability that kappa I takes on the specific value k. That makes a little bit more sense, I think. So we're going to change this integral and write it as a sum. Okay, so now we have the free variable k, so this is probably like kappa equals k, and then this is going to be, again, kappa I equals k. Is everybody good with that? Okay, so now you can see that we can actually fill in some of the blanks. So this was one of the equations that I put in a blue box. This is probability of kappa given xi. So that was, where was it? That was this one. Okay, so in this expression, we don't have any prior information. So we're just writing this based on these statistical values here. The only difference is down here, we're saying, when you do that, use the guesses from last time. So here we're using the guesses from last time in writing all those variables. And we're going to give this a name because it shows up a lot. We're going to call this guy gamma ki. The interpretation is that this guy is your belief that the ith sample is in the kth cluster. So when this is large, it means, yeah, I do believe the ith sample is in the kth cluster, otherwise it's not. And this is just your belief at iteration t of running this algorithm. So now we have a log, okay, so now we have a joint probability, joint over x and kappa. We can write that as x given kappa times the probability of kappa. And that makes our lives easier because this probably x given kappa, we know that that is just a Gaussian. And then this is the probability of kappa. We know that that's just, we call that lambda k. So we have reduced this Q to a double sum over terms that we know about. I should also emphasize that over here, we're using the variables that we're going to optimize over. So these guys don't have the superscript t, whereas these do. These are old variables we can compute. These are new things we don't know yet, but we can maximize them in the M step. Okay, everybody with me so far? Okay, so here's the M step. This is the Q we just derived on the previous page. Let's see, so what we did is we have double sum, and we're doing a log of a product, so that's going to give log of the first plus log of the second. That's how we got two terms. So here log of the second is this term, log of gamma k, and then log of the first, that's log of the Gaussian, that's this term. And so we need to maximize this expression over all the unknowns. So this is going to take us a little bit of work to do. We have three different kinds of unknowns. We'll optimize them one at a time. So the first is we'll first handle the lambda k's. We need to work on them together because they're coupled. They must sum up to 1. So we can't just optimize one at a time. We actually have this constraint. Okay. And then later on, we'll work on the other ones. Okay, so we learned about a way of doing constrained optimization where we want to, so this is actually the only thing we need to optimize here. This is the only place our lambda k, gamma k's show up. So you want to maximize that, but subject to this constraint. So we learned this Lagrange technique to constrained optimization, where you take the original unconstrained cost and then you introduce this Lagrange multiplier, and then you rewrite the constraint in a way that it equals 0. So this guy we can rewrite as 0 equals 1 minus sum over the lambda k's. So this is actually what we're using here for our constraint. This is our Lagrange multiplier. Our first task will be to figure out what is the value of this Lagrange multiplier. So one thing we know is we know that we just set the derivative of now, this is our new unconstrained cost. We set the derivative to 0, and that will give us the optimal lambda k. Okay, so let's see. So for the first thing, okay, let's work on this first term. So we're taking the derivative with respect to gamma k. And we have this whole sum of many different gamma k's, but I'm only interested in the kth one, not all the different k primes. So only one of the k primes will match k. So at that point, I can get rid of the sum over all the k primes. And I'm just going to focus on the one that says k. And then when I take the derivative, we know derivative of the log is 1 over. So that gives us this term. Then derivative of this is a little bit easier. That's going to be lambda minus and 1. So minus lambda. So this needs to equal 0. So let's rewrite this by multiplying both sides of this equation by gamma. So we get this. And so here's a little trick. It's kind of unintuitive, but this is often what you do in these Lagrange problems. If 0 equals this, then I can sum both sides across k, and that's still going to agree. So the sum of zeros is 0, and the sum of this, well, you can see I have the sums over k. The reason I'm doing this is we know things about the sum of gamma k. We know that this must equal 1. So that means that this whole thing can be replaced by 1. And moreover, we know that for all these guys as well, if you fix I and you sum across k, that must also equal 1 for every I. So what's nice is now we just have a sum over I of 1, and we have a minus lambda sum over k of 1. Actually, just minus lambda. And so over here, we're actually summing from I equals 1 to n. So that gives us n minus lambda equals 0. And finally, that tells us our Lagrange multiplier, lambda is n. We can plug that into here. And so I can move this to the other side, divide both sides by lambda, I get this. But now I plug in lambda equals n. Now I can see that lambda k takes on this value. So I figured out how to optimize my lambda k's. So we're done with that. Okay, is everybody good with that derivation? Okay. Next one is we want to maximize over mu. So this will be the thing we care about. We want to set the gradient of that to 0. So gradient of this with respect to mu, set that to 0. So here, we know that the log of a Gaussian is very convenient. There's a scale term that does not depend on mu, call that constant. And then we have a quadratic form inside an exponent. So when we take the log of that, we just get the quadratic form alone. And so now, because the gradient is linear, I can move this to the outside. I can move my gradient, focus it on this. And this is something I know you guys have seen in some homeworks. So a shortcut with vector calculus, whenever you have something like A transpose C, A transpose, and you want to take the gradient of this with respect to A, always remember that this is just 2CA. So that's what we're using here. Basically, we're using that. And so essentially what's going to happen is we're going to get this part, and there's going to be a sign change because of the minus here is going to cancel that one. And so finally we get this for our gradient, which means this is whole expression equals 0. So we can rearrange it, make our lives a little easier. Let's pull out this term. Basically, this is a scalar, so we can move that through. The sum is over I. This is over k, so I can move the sum through. And we have qk inverse times this. We want to set that to 0. You guys see how we do that? How do we set this to 0? Because we don't know qk, right? So as long as the inverse exists, that means that this matrix is full rank, meaning there's no way I can multiply it by a non-zero vector to make it 0. So the only way to make this times something 0 is to make the vector itself 0. So if this equals 0, then that means this equals 0. So then we're almost done. We just have to, so we set this expression to 0. To do that, we can divide both terms by this scalar, and then mu k equals this. So now we have our expression for mu k. That's going to be what we use in the next iteration. There's a similar optimization for the matrix, but I'm not going to get into that. So to summarize, oh yeah.
Is there a reason why the I and K switch places in the subscript on gamma?
Just a typo. Yeah, they should be the same. Yeah, good catch. I'll try to fix that, I guess. Yeah, I need to be a little more consistent here. Okay, so that's it. Basically, we know the EM algorithm. So you repeat these 4 steps. The first step is you compute these, think of them as membership probabilities for every sample. It tells us across the different clusters, how confident are you that it's in those different clusters, and these numbers add up to 1 across clusters. Once you know those, to get your overall gamma, you just average over these guys, average those over the samples. And then to get your overall mu, you take like a weighted average of those points xi, where you're weighting, so for mu k, you're weighting the ones that you have more confidence land in cluster k. So just kind of a weighted mean. And then with the matrix Q, it's just a weighted outer product. So it looks like a sample covariance, or weighted sample covariance, basically. So that's it. That's the EM algorithm for Gaussian mixture modeling. Now, it is important to start with a good initialization, otherwise you can get stuck. So it's common to use k-means plus. So as we know with k-means plus, you're going to get a vector of clusters. So what you can do is you can, and also, in addition to a vector of clusters, for every one of your data points, you get an assignment. You know which cluster it fits into. So if you just look at how many cluster points were assigned to K, like what fraction was assigned to K, that's a good initialization for these probabilities. Because remember, these are basically like the elements of the PMF of kappa. So for cluster K equals 1, you just look, maybe 1/10 of my samples landed in that cluster according to k-means plus, so I'm going to set my EM initialization to 0.1 probability that those values land there. And similarly, like you can use those exact same ratios. You plug those into here, and you get initializations for your mean and your covariance. And so that's basically it. And then you just iterate. I'll show you a pictorial demo on the next page. Any questions on procedure? Yeah.
What's the standard stopping condition?
I think, so for sure, let's see. I don't know if there's like a universal approach, but, maybe I would look at how much the means are varying from one iteration to another, and I'd have a threshold on the norm of the means. That's probably how I would do it. Once the means from one iteration to the next are changing like below a certain level, I would just say it's time to stop. Yeah, that's a good question. There's probably different criteria for how to do that. I don't know exactly how sklearn does it. You could look at the parameters you specify, and you might get some clues to how do they terminate. So a comment, though, is that one issue in doing this is, this is a D by D matrix. So if you have many features, dimension D is large, this is a large matrix, and estimating matrices, you just need a lot of data. Generally speaking, if you have a D by D matrix, you need roughly at least 10 D samples in a sample covariance matrix to get a reasonable estimate. So, so depending on your dimension, like if your dimension is, 1,000, you would need at least 10,000 samples to estimate it well. And it would be kind of compute intensive. You would have a matrix of 1,000 by 1,000, which is 1,000,000 parameters. So what often people do is they just say, let's just pretend this is a diagonal matrix. So you're just estimating the variances of every cluster. Basically, you're saying the clusters are circular instead of elliptical in terms of their shape. And then it runs a lot faster, and it requires less data and all that. So that's a very common approach. And it's one of the options for sklearn. Okay, so that's that. Let's look at a little pictorial example from this book by Bishop, which is a really nice book on machine learning that has a bit of a Bayesian flavor. So this is the first iteration. This is your data points. They just come at us without any labels, any clustering at all. And these represent how we initialize our Gaussian mixture. So we're going to do a mixture of two Gaussians. We're going to put the center of one here, and this shows the contours. So we're using an identity covariance initialization, and so we're going to have a circular contour. And then the other one we're going to put over here. And notice we're kind of making the initialization kind of difficult because you can see we probably want to put clusters here, but we're actually initializing in the orthogonal direction. So it's not really clear what's going to happen. Okay, so at the very first step, we compute these membership probabilities essentially by saying, okay, we have some guesses of these. how close are our samples according to that guess. And yeah, so like for this, you'd say, like for every sample, you'd say, like, how close are these samples to this Gaussian? So here we're plotting those gamma values. The gamma values are, gamma I, k are in the interval between 0 and 1. So we're going to plot them on a color scale from blue to red. So when gamma is close to 0, it's going to be very blue. And gamma is close to 1, it's going to be very red. And at least, okay, the way this number is 1 when it's red and 0 when it's blue. So as you can see, the samples that are closer to the center of this Gaussian get more blue. The ones that are closer to that Gaussian get more red. And there's sort of like a decision boundary, which is right between those Gaussians. It's going to be linear in this case. That's going to be kind of the decision about whether it's red or blue. And now these colors, the colors are these values, and they tell us exactly how to weight the points. So now imagine you're going to do a color-weighted averaging of these samples. So any samples that are blue really count towards your average. Any samples that are red don't really count in your average of these points. And so as a result of doing this, you have a new mean for the blue around here. You do the same thing for red, and for the mean, for the red, you get a mean here. And also you do that for the covariance, and you get this covariances that have these stretched ellipses like this. So this is what you get after the first iteration, L equals 1. Is that kind of clear how that happened? Okay, now that you have these new ellipses, you come up with a new color labeling where you take all your points and you say, how close are these points, to this Gaussian? How good of a fit are they to that? That gives you new blue labels, and then how good of a fit are they to that Gaussian? That gives you new red labels. And now you can see that the redness has shifted a little bit more in this direction, and the blueness a little bit more in that direction. And you just keep iterating this. This is after 5 iterations, after 20 iterations. And you see that gradually these Gaussian ellipses have moved over so that this one is indeed centered there, this one is centered there. And you can see that it also tells you a little bit about the shape of the cluster. Not just that the cluster is centered here, but that the cluster actually is stretched in that direction. And this one says the cluster is stretched here. So that's really the difference, one of the main differences between k-means and EM. EM not only tells you the centers of the clusters, but actually tells you how they're shaped. Whereas k-means doesn't even try to do that. It just basically tells you what the centroids are, and that's it. Okay, so this is just sort of seeing the algorithm in action, and it is converging to a pretty good labeling, I would say. Also, as these guys get smaller, because the tails of the Gaussian decay very quickly, you get a pretty sharp boundary. So this is very red, this is very blue. The boundary between red and blue got very sharp. So that, as these get smaller, that will be sharper and sharper. Okay. All right, so that's that. Any questions? Yes?
If you continue to run more iterations, will those ellipses get smaller, or is that the end where it's...
I think it's just going to kind of settle out there, and it will just not really change much from that point on.
Okay.
Yeah. Okay, so we have now 2 approaches that are similar in many ways, but a little bit different. So let's compare EM, GMM to k-means. Okay, so one difference is that EM is computing soft assignments, probabilities for every point, whereas k-means is computing hard assignments, just one cluster index for every point. So EM is giving you more nuanced information. EM is estimating full covariances that tell you how the clusters are stretched, whereas if you look back at k-means and you try to make this correspondence, you can kind of deduce that k-means is implicitly using identity covariances scaled by a very small epsilon. That's basically, you could say k-means is doing that. So as a result of this, EM is using piecewise curved decision boundaries, whereas k-means is using piecewise linear. So if you remember, with k-means, we said that you had boundaries that looked like this. For example, if you have those centroids, so those Voronoi cells, they all have linear edges. But when you do EM and your covariances are different, then what's interesting is the boundaries are no longer lines. They're actually curves. But they're piece curves. So like maybe if I had another one over here, then what you'd see is you'd have, well, you'd probably have one like here. So up to here is one curve, and then this is another curve. So piecewise curved. So it's more interesting boundaries than k-means. EM also estimates the weights. It tells you how many samples, roughly, what's the probability that points end up here versus here, whereas k-means doesn't. It implicitly estimates same number for all. The EM iterations are computationally more expensive. You have to compute those covariance matrices and stuff. Both can get stuck in local minima. Both benefit from good initialization. And both are implemented in scikit-learn. So here's like how you do it. So Gaussian mixture, you instantiate this. You tell it how many components to fit. You tell it whether you want to do diagonal covariance matrices or full covariance matrices, how many iterations to run max, how to initialize. We'll initialize using k-means. Then, once that's instantiated, you just do .fit. It computes all that stuff internally, and then you can give it your image, your data, and it will predict the labels for that. So it's easy to use, just like all the k-means stuff. And, okay, so any questions on these two? Yeah.
Yeah, I have a question and then maybe a follow-up.
Sure.
So when you say you can get stuck, is it in local minima or maxima?
Well, if you are maximizing the likelihood, then it's getting stuck at a local maxima. If you're minimizing the negative log likelihood, local minima.
Okay, and then
Yeah.
the follow-up was, I guess, kind of back to the basics of these. Why do we choose maximization? Is it just because we don't know that it's convex, so it's not?
So the likelihood is, we want to maximize the likelihood, maximum likelihood. So if we would have said negative log likelihood, then we would be minimizing. It's just a choice for how we name it. They're equivalent.
Yeah.
So for some reason, expectation maximization historically focuses on maximizing it, maximizing the likelihood. So if somebody would have named it, expectation minimization, maybe they would have been focused on minimizing the negative log likelihood, and then probably my slides would have reflected that in writing the negative log likelihood and minimizing it. I'm just trying to be consistent with maximizing the likelihood, but they're the same.
And then in the earlier modules, was it easier to minimize cost, or would it have been the same if we chose maximization?
Would have been the same, more or less. I mean, so here's one of the issues. So now because we're doing the log likelihood, we have a negative sign. So you could say it's kind of ugly. Do we really want to maximize this negative quantity, or do I just want to minimize this quadratic positive quantity? So I think it's a little more elegant to not have that and do minimization. So I think that would be the argument. Like RSS, there's no minus sign, right? Yeah. Unless you get to sklearn, and then it's negative mean squared error, right? Because it wants to maximize, because it says here's all the metrics. For all metrics, they should be maximized to be consistent. So that's why they call it negative MSE. Yeah, but it's minimizing MSE. It's the same thing. Okay. All right. Any other questions? Okay, so we have this kind of interesting demo. It's kind of a neat demo because it's not something you might initially think you could use clustering for. But so this is what we have. So we have an image, color image. Almost all color images use 8 bits for each of the red, green, and blue channels. So when you load this color image, you'll have 8-bit integer data. So 8 bits for each color channel, or 24 bits total per pixel. And so if you ask how many different color possibilities do you have? It's a lot. It's 2 to the 24th, which is 16.8 million possible. So that's basically why 8 bits is enough, right? There probably are, I don't know all the different standards for maybe video and so on. They probably use more than 8 bits for some, but you can already see with 8 bits you can get a lot of colors. But let's say that for whatever reason, like we want to do compression. So we don't want to use 24 bits per pixel. I want to compress this image, color image, down to 4 bits per pixel. So what that means is I will only be able to create 16 colors. I'm saying I want to represent this with 16 colors, but I don't know what my 16 colors are going to be. I'm going to pick those depending on the image. So we can think of this as a clustering problem. We can think of our feature vectors as d equals 3 features. So every sample that I get is going to be 1 pixel in this image, and it's going to have 3 values. And my goal is over all those pixels, all the samples, I want to come up with 16 centroids that I'm kind of clustering all that data. So 16 centroids, these are going to be 16 good colors that are in some sense close to all my data points. Like trying to figure out what 16 colors are close to all my pixels. So this particular image we're working with here has 273,000 pixels. We could run these algorithms on that many, but it might take too long. So I'm just going to choose 1,000 pixels at random from this image and do the fit on those just to speed things up. So I'm going to have 1,000 data points. Each is going to be an RGB vector. And I want to find 16 centroids that best match those 1,000 feature vectors. Does that kind of making sense how we're doing compression with clustering? Okay. So now I have 2 algorithms I can do this with. I can run EMGMM and I can run K-means++. What do we hope happens? We hope which one is better? Yeah, we spent a lot of time on it. It's a lot more complicated, right? It has all this probabilistic stuff. Like, hopefully there's some reward at the end of the day. Okay, let's take a look at the original image. So the things we should notice here is that we have, like, if you look at the sky, there's a very nice smooth gradient from blue to pink, and vibrant colors, all that stuff. You can see around the horizon, there's particular details, like there's an island here, there's a bridge to the island, there's land, there's water, there's boats, and so on. So when we do quantization with a GMM, we're basically picking 16 colors, and only 16 colors we have to represent all pixels by. So, like the colors are not as vibrant anymore, for sure. The sky basically now is represented by 3 different colors instead of, tons of colors. And probably what's most interesting is what happens around here, around the horizon. So at least with the GMM, you can still see the island, you can still see the bridge. Although if you saw this alone, you might not be able to really guess that was a bridge and an island, but you can kind of still make them out. Okay, so now when we do this with K-means, overall it's similar. There's the sky is 3 colors, but you do see that like some of this stuff was just not done as well. You can't really make out the island or the bridge anymore. So you can still see the boats. Boats are little blips, and the water has basically 2 colors for the water and so on. But I would say that GMM is a little bit nicer, as we would hope. So, all right. So we're almost done. I think the only thing left I wanted to talk about is a couple of things left, just 2 more slides. So just notice that all throughout our discussion of these both, we had to tell it how many components to cluster into. But in practice, maybe you don't know that, right? Someone gives you a data set, you're like, well, should there be 2 or 4 or 8, or how many should there be? So for that, there are methods that can handle that. So these are some methods, more complicated methods, but it is just something to point out that for these 2 methods, we really did have to just tell it how many clusters to use. Another important question is like, what features should we use for clustering? Like, should we be using the raw features like we have been? Or like what we learned when we were doing regression and classification is that if we use an SVM that had this kernel, we get much more interesting features that were much better for clustering. The same is true here. you can do clustering with kernel methods, and it's called spectral clustering. And those methods work really, really well. Okay. And sklearn has a lot of really nice documentation. If you look up their documentation on clustering, they talk about a set of methods, and they have these nice little pictures that show for certain kind of standard. This is all really low dimensional stuff, right? 2 dimensions. They show for certain 6 different cases what's going to happen. So here's Gaussian mixture, which we learned about. Here is mini batch k-means, so think of that as k-means. And then a bunch of things we haven't talked about. So here's spectral clustering, which is computing features that are hopefully going to work better. And there's a bunch of other methods. So let's just look at the first one. If you're given data like this, what's k-means going to do? It's going to have to come up with 2 centroids, right, in the raw feature space. And you can see, because of the way that this data is structured, it's not linearly separable. So, k-means is going to do something like this. Put a centroid here, put a centroid here. And as a human, you'd look at this and you'd be like, that's probably not a very good clustering. I can be smarter. As a human, I might cluster something like this. And in fact, that's what spectral clustering gives you. It's able to bring the data to a higher dimensional space, and then in that space it's linearly separable. It can do a nice clustering, and maybe that's how we can understand it. Gaussian mixture is no better than k-means here. And then you have a number of other methods, like dbScan does a good job, the Galometer clustering does a good job, but this doesn't do a good job, these don't do good jobs, and so on. Then you can look at this 2 moons data here again, you hope that you get stuff like this. Maybe as a human you could do that. Mini batch k-means is going to come up with linear separation. Same thing with Gaussian mixture. But some of these other methods do a pretty good job. Spectral clustering, some of the other ones. And then we have these data sets like this, which you can see k-means is not doing a very good job. But Gaussian mixture is, because Gaussian mixtures can essentially come up with different cluster sizes and shapes, right, as long as they're ellipsoidal. So it's doing a good job with this data, much better than k-means. These other methods are doing a good job too. Actually, this one is not. This one missed those 2, right? I just put those all together. So what about these? So this is perfect for Gaussian mixture because you have these stretched clusters, and you can see a lot of these other methods are really having trouble. This one is working. This one is not. This one is okay, but it's messing up there. K-means terrible. This is an easy one. A lot of methods. I think they all do well in that. And then this is a super hard one. What happens? So k-means, Gaussian mixture do terrible. Some of them kind of get it right. They just pick the same for all of them. Same color for all points. So it's sort of interesting. Gives you a bit of intuition. But this is all low dimensional stuff. Generalizing to high dimensions, doing clustering in high dimensions is much more complicated. And there are some neural network approaches now for how to do this. Pretty interesting stuff. Spectral clustering you can try in high dimensions. It doesn't work super well. It kind of works. Okay, and that's all I have for these notes. Any last questions? Yeah.
How could you even verify high-dimensional clustering?
That's a great question. So you set up problems that make sense to humans. So it's like you give it a data set of dogs and cats and different animals that are unlabeled, and what the labels are, and then you give it to this algorithm and you say, can it figure out how to label the data? And that's hard because dogs and cats, you can imagine, you can find dogs and cats that have the same kind of fur, right? So it really has to focus on some what we call semantic features, particular things about the shapes of the ears and the eyes that are hard to do, right? But it actually, these neural network methods, they work great for it. That you give them ImageNet, and a good one can figure out ImageNet labels pretty well, without any guidance. So it's kind of amazing. It's a lot about coming up with features that you can, this is what we call self-supervised. It's like somehow it has to learn, it has to figure out its own way to think about the data. And so there's some nice methods to do that nowadays, so-called self-supervised methods. So yeah, but it's a cool problem, definitely evolving. Okay, any other questions? All right, okay, well, thanks for attending all these last lectures. The brave, the few, the strong. And that's it for, I don't have anything more, so no lecture on Monday. Good luck with your projects. And